In the second item, we are to find the shear and moment diagrams for the beam loaded showing, noting the important features. Reactants have already been provided to us. The keys, of course, are going to be that the slope of the shear diagram, variation of shear, is given to us by the load intensity, and that the slope of the moment diagram is given to us by the value of the shear. Our units for shear are going to be kips. We know that, of course, because it's a force quantity. We start off at 0, and we have an instantaneous change to a plus 24. So, bam, there's our plus 24. Then we have a downward slope of 3 kips per foot over 75 feet. So delta V between these two places, let's call that A and B, then would be equal to a minus 3 kips per foot times 25 feet. That's effectively that area, and so that's a minus 75 kips. 24 minus 75 is 51. So we will go and get that one in there. There's your minus 51. The 0 point, of course, is going to happen where we have 24 kips divided by 3 kips per foot, and that will give us 8 feet to get from there to there. That's an important location. And then, by the way, that would leave us 17 feet over here on the other side. Now we go from 51 and we go up by 96, so that will leave us a net of 45. Right, so a delta of 96 up, and then we hope that that closes off. Let's see that if it really does, back to 0, because this area then would be a delta V equal to minus 3 kips per foot times 15 feet. That would equal to minus 45 kips, exactly what it should be to get us to close off. We have nothing but straight lines, and we got everything dimensioned and units, so that looks good. All right, so now let's check out the moment. The moment is going to be in kip feet because, of course, moment is equal to the integral of V dx, and we got kips for shear times length units of feet, so that will be in kip feet. That sounds good. We have a pin support at the left, so we start off with a 0 moment. There's no applied couple. We're going to go from a first order curve and integrate, ending up with a second order curve. That's true in every segment that will end up with a second order curve. We have a 0 slope for the moment happening here at 8 feet over. That's because, of course, dm dx, the slope of the moment diagram, is given to us by the value of the shear, so we're going to have a 0 there. That change in the moment will be given to us here. Integrate the shear, so 1/2 of 8 feet times 24, that would equal 96. That is of course, positive area, so we're going to go up to 96. That's the delta, but we start off at 0, so we'll be up to 96. Now, before I go draw that and even do anything, let's find out what's going to happen next. We have a minus negative area here, so the delta m for there is going to be minus 51 times 17 divided by 2, and that is a value of times 17 divided by 2, 433.5. Again, that's a negative value. Right, so that'll get added back to the 96 because that's the incremental change. We'll have a change down to negative 337.5. So let's see here. With the scale that I seem to be choosing, then that might be around in here. Get feet there, and then 96 would be about in here. And so we'll have a second order curve that starts off with a big positive slope at the left, 0 slope at 8 feet, and then it ends up with a negative 51 kip foot per foot over here. So now we got be thoughtful and careful about how we pull this out. We want zero slope where the maximum is. We have a constant rate of change of the moment, so that means we actually have a symmetric looking kind of thing going on here. So 8 feet on either side is going to be where we approximately end up going across, not approximately, that is where the zero moment is located. So that's just kind of helpful as we try to figure out how we're going to lay out a curve that's about what we're supposed to have. I'm going to do this in a different color to help it stand out a little bit, and then just turn that over, try to get zero slope there, nice and smooth and continuous. Sometimes it's hard to do that. Looks like I did a pretty good job on that one. And then we got to finish this thing off. We've got a slope at the just to the right of the support of a positive 45 kip per foot. It goes to 0. The area or change in moment will be 45 times 15 divided by 2, which is equal to 337.5. So that's good. It does exactly what it's supposed to and closes off to 0. It's a second order curve. So now we just get in here something that has a nice zero slope at the right and gets us where we want to be. Looks to me like we have done a pretty good job of indicating the important points. That's the maximum where it crosses 0. We've got the order of the curve. We've got zero slope where we're supposed to have it, not zero slope everywhere else. We're not supposed to have zero slope. You know, all that's looking ultimately just like it should.